In this video, we're going to start section 5.3. This deals with Euler's theorems and what's called Fleury's algorithm. So if you remember what an Euler circuit is, so an Euler circuit is going to be a circuit that travels every single edge in the graph once and only once and goes back to where it starts. So the idea behind an Euler circuit is that if we're looking for a solution to a street routing problem, like maybe you're the mailman that wants to drive down every street once and only once, if you can find an Euler circuit, then you have solved that problem. So sometimes graphs don't have Euler circuits. So here's just a theorem to show us what to look for. First of all, our graph has to be connected. If it's not connected, it can't work. And then every vertex is even. This means an even degree or an even number of lines coming off every vertex. If we have these two things, that we're guaranteed to have at least one Euler circuit. If any vertex is odd, it does not have an Euler circuit. All right, so if we look at these three examples, these are going to be three separate graphs. If we look at the first one, notice that this one is not connected. Okay, it is in two components. So we would say it does not have an Euler circuit. So no Euler circuit. Now if we look at our second example, we do see a connected graph. So we want to go through and we want to count to get the degree of each one. And I'm just going to write the degree right next to the letter. So the degree of A is 2, B is 1, 2, 3, 4. C is 1, 2, 3, and we can keep going or we can stop. Let's go ahead and do the others. 1, 2, 3, 4 for E, 1, 2, 3 for D, and then 2 for F. So notice right here we have odd vertices. So according to the theorem up above, that guarantees that we do not have an Euler circuit. So I'm going to say no Euler circuit. So the reason for the first one was that it's not connected. The reason this time is we have odd vertices. So if we look at our last example, we're going to go through and count our lines. So A has degree 2, B has 4, C has 1, 2, 3, 4, E has 1, 2, 3, 4, D has 1, 2, 3, 4, and F has 2. So notice they're all even. So we can say yes, it has an Euler circuit. Okay, and our reasoning for that would be all even vertices. So the idea is that as we travel along an Euler circuit, we'll always need even vertices, so we can use one edge to go in and then one to come out. So if we get stuck with an odd, we'll get into a vertex and then not be able to leave. And so now we're going to look at Euler paths. Now those are a little different because you get to start and end at different places. So this theorem says if the graph is connected, just like before, we have to start with a connected graph. If the graph is connected and has exactly two odd vertices, then it has at least one Euler path. The path must start at one odd vertex and end at the other odd vertex. If the graph has more than two odd vertices, it cannot have an Euler path. So this is a little different. We want all even except for where we start and end, and those can be odd. Okay, so if we look at the examples above, this one's not connected, so it can't have a path. This one was all even, so it had a circuit. But notice this one, it had two odds. So we should be able to find an Euler path, meaning maybe we start at D and end at C or vice versa. We can find a path where we travel each edge once and only once. So we'll say the middle example above has an Euler path. Now, part of the problem is when we're counting, it's really easy to miss a degree. So this is a little theorem to kind of help you with that. It's the Euler's sum of degrees theorem. It says the sum of all the degrees of the vertices of a graph equals twice the number of edges. Okay, and if it's twice the number of edges, that means it's always an even number. Now that may not seem that interesting that the sum of the degrees is even, but what we can conclude from that is anytime we have an odd vertex, there has to be another odd vertex to match it. So we'll go ahead and reword this as odd vertices come in pairs. So when you get done counting all of your degrees, you want to make sure that all your odd vertices pair up. If you have an odd number of odds, then you have made a mistake somewhere.